We've exhausted Unit 1, and we will go into Unit 2. Joachim?
Yeah. You continue?
I continue? Okay. So maybe around noon or something, I give it back to you? Or try to okay. Okay. Okay, so this Unit 2, Chapter 2 is on advanced techniques, which Joachim will cover. So this 2.1 is kind of intermediate between beginner and advanced, maybe, and it talks about some mathematical techniques for preconditioning. It could be useful if you want to solve your problems faster using your own preconditioners. Knowing how the usual preconditioners are built into NGSolve allows you to extend it to problems that you want to solve. So here are some built-in preconditioners. If you want to, the 2.1.1 is on standard preconditioning facilities given inside NGSolve, and then the next one we'll see how to tweak the standard facilities, and at various levels of sophistication. So the built-in preconditioners include the Jacobi preconditioner, which is in NGSolve is called the local preconditioner, or a block Jacobi, which we'll see, I think, in more detail in the next tutorial. There are direct solvers, which of course you can use as preconditioners, but that's usually overkill, or it doesn't work if the problem size is too big. There are geometric multigrid smoothers, which are very interesting. Using a keyword multigrid, you can access them, or algebraic multigrid preconditioners using the keyword H1AMG, and BDDC preconditioners that you can access using BDDC keyword.
Shane will go into geometric multigrid preconditions tomorrow, right?
For fancier spaces, I think, right? Yeah. So this is only on the Lagrange space. I'm not stealing your thunder. Okay, so here's a simple test problem where we solve the Poisson equation. It's put inside a method so that we can keep using it for various mesh sizes, polynomial degrees, number of refinement levels. You start with a coarse grid and refine a certain number of levels, and with static condensation on or off, and whatever preconditioner you like. Okay. Inside the solve routine, you see the same type of statements you've seen before. We make a mesh, we make a Lagrange finite element space, and we make the bilinear form and the linear form. And what is new here is this. A preconditioner object is created before the form is assembled. And then that preconditioner object is being used inside the solver here. So the solver is provided with both the original linear system matrix A and the preconditioner. And inside the preconditioner goes the flag that tells it whether you want to use local, multigrid, or whatever preconditioner. The rest of this is pretty self-explanatory. If you want to solve in level at a certain refinement level, then you take the mesh and refine it as many times as you want, and then solve it, etc., etc. And if you want to condense, then you do the static condensation steps, otherwise not. Okay, so let's start with the local preconditioner. We take this problem and solve it using a point Jacobi. Local preconditioner is just taking the diagonal of the matrix, invert the diagonal of the matrix, and use that as a preconditioner. Okay, it's not a great preconditioner, but it does do something. I'm sorry, I didn't execute this. And I forgot to point out that this routine returns two numbers. The numbers it returns are number of degrees of freedom and the number of iterations done by the conjugate gradient, preconditional conjugate gradient. Okay. So here, going back here, the number of degrees of freedom is ridiculously small, 8. And the number of iterations is also small. If you go up to 9 levels of refinement, then you are solving larger problems, as you can see, from number of degrees of freedom to 8 to 197,000 degrees of freedom, and these are the number of iterations. The number of conjugate gradient iterations goes up considerably. So not only is each step more expensive, but you must also do more steps. This is the double whammy problem of not having a good preconditioner. Okay, if you use a different, more powerful preconditioner, multi-grid preconditioner, instead of the point Jacobi or the local preconditioner, you just need to change the keyword preconditioner argument keyword argument from local to multigrid, and you see the number of iterations are pretty much constant. The problem size has gone up, and each step is more expensive, but the number of steps is constant. Okay, and here's the difference in pictures. Oh, it's not really fitting, but the local is the point Jacobi. The number of iterations plotted here is going up, whereas for multigrid, the number of iterations flattens out. Okay, in NGSolve, the multigrid for high order spaces, it uses the lowest order multigrid and then some smoothing techniques. So to explain this, here's a high order space where H and P are varying, and here is the subspace, the finite element subspace with the lowest degree, P equals 1, and then you have these subspaces with edges, faces, cells, and so on. And you can decompose the matrix, the matrix which you want to invert and solve the problem in this block partitioning using the vertices, edges, faces, and cells. So the multigrid implementation for a high order method uses an H version multigrid for the lowest order block. The H version multigrid is just multigrid on the P equals 1 block. And then we do these local block smoothing for high order bubbles and functions. Okay, so we again call this problem this function, but now what we are changing is the polynomial degree. We're changing the polynomial degree from 1 to 10, and you see how the degrees of freedom are increasing and the iteration numbers are also increasing, perhaps somewhat mildly, but it is increasing with degree P. If you do static condensation, now you turn on this flag, then this gets a little bit better. You see, instead of these numbers that the 20, 29, 30, and so on, you see better numbers here, and they seem to have stabilized. Okay, now another general purpose preconditioner in NGSolve is the BDDC preconditioner. There's a whole other tutorial on it, but let's just see how to use it without knowing what's inside. We just put this flag, preconditioner equals BDDC, and then we do the same experiment we did before with varying polynomial degrees, and you see the number of iterations are more, but this preconditioner, each iteration of this preconditioner costs less than the previous one. So this is each step is cheaper, but you have to do more steps. So and this element-wise BDDC preconditioner is very good for both shared memory parallel architectures and distributed memory architectures. So there's more about this in this tutorial, and depending on time we'll decide whether we go into that or not. Questions?